And I will give you information. I will explain you how certain information can be represented in a database when it is not obvious or intuitive. Okay, so you can see the complete list of topics below, but I will not read it. So let's begin. Okay, I hope you can see the slides moving because I read something strange in the chat. So I'm actually changing the slides. I don't know if you can see it. So let's define the criteria when a database design is good or it is not. Oh, I read that my photo is covering the slides. Is it better now? Did the photo disappear? Okay, good. So let's continue. So let's define the criteria when a database design is considered good or not good. First of all, keep in mind that sometimes it is subjective, okay? So the same design could be good for certain circumstances or bad for others, and good according to some persons or bad according to others. Anyway, general criteria that should be acceptable are queries should be fast. I think that everyone agree on this. And then the data structures themselves should be reasonably simple and reasonably extendable. Extendable because, you know, the requirements change over time. Developers can be asked to add or remove features in their applications, and they must be able to do it without changing the database design completely. But this kind of conflicts with simplicity. So sometimes it is a trade-off that you have to find based on common sense, based on your experience, and so on. So let's move on. I think it is fair to spend some words about why we are going to talk about relational databases, because, you know, there is a strong NoSQL movement, not as strong as it used to be some years ago, probably, but still NoSQL databases exist. They are good. And sometimes it is not obvious why you should use a relational database or a non-relational database. I think the generic thing to keep in mind is NoSQL databases are generally good for specific cases. They are designed generally to do something specific. For example, Memcached, which is very old, so it predates the NoSQL movement. It is obviously designed to serve as a cache. Cassandra is designed to store data in a sort of key value model, but allowing group by and order bys, and it's designed to write very fast. But at the same time, it is not extendable. So in Cassandra, you define a table keeping in mind how it will be used. You keep in mind how you'll filter data, how you will order data, and if you want to run a completely different query with a different filter and a different order on the same data, you will have probably to create another table with another primary key on the same data. So the relational model is surely the most flexible. This could sound surprising, but if you think about it, actually, first of all, you are sure that when you insert data and the database returns okay, the query succeeded, you are sure that the data is persistent. Even if something bad happens, even if the server crashes, your data is there, which is generally what you want. And also, you typically design tables keeping in mind how you will use them. And if at some point you will need to use them in a completely different way and run a query that you didn't have in mind previously, well, most probably you can. Maybe you will have to add another index, but it will work and probably it will be fast. Okay, well, here I made an example of this kind of flexibility. Basically, here we have a user table. We have a couple of queries to extract data, first by ID. Probably initially we only thought about extracting data by ID, which is the primary key, and obviously the first query is fast. The second query is not fast because we are accessing the table by email. So what we are going to do is simply creating a secondary index. You can see the create index statement. And basically, after that, we will be able to run the query we need. But there are also cases when the relational model is not a good fit. Some obvious examples are heterogeneous data. So for example, when you have to store a catalog of different products with different characteristics, it doesn't mean you can't. Toward the end of the webinar, I will show that there are ways to do it. But it's true that the relational databases are not necessarily the best way to do it. Other examples are searchable texts, graphs. But again, this is mostly historically true. But if you think about it, more recently, all relational databases, at least all the most common relational databases, added some non-relational features to allow to do these kind of things. Probably not efficiently as more specialized technologies that are built to deal with these use cases, but still you can do them. So example of these features are inserting JSON data into relational tables, having a proper JSON type and JSON functions, using arrays. This is a very old feature from PostgreSQL, for example, and also full text indexes, and so on. So let's talk about what is at the core of relational databases, which is keys and indexes. But let me say first, this is a not trivial topic. So I will not explain in details how to use indexes, how to build proper indexes for your queries. I could do this in a separate webinar. Now there is not enough time, unfortunately. But I will give you an overview and I will show you best practices that a lot of people follow and you don't want to follow, hopefully. Let's move on. Okay, so first of all, primary key. The primary key is a column or a set of columns that identify each row. So it means that every value of the primary key is unique and it's not null, okay? Because if it's null, you cannot use it to retrieve a single row, right? Null simply means unknown value or missing value. So typical examples of a primary key are the ID column, which is almost always numeric, and UUID, which is usually, well, a string with a quite long string, or better, a series of 4 bytes which identify a which is okay, sorry. It is basically designed to be almost certainly unique, okay? Because if you generate a UUID, you do it based on which server it is running on, it is based on which moment in time it is, and so on. So it is very, very, very unlikely that two UUIDs are equal. Let's move on. So I want to show you some poor examples of primary keys. The first is obviously no primary key at all. If a table doesn't have a primary key, it means it doesn't have a way to, at least, a way to identify each row by design. Okay. In MySQL, this will also cause several performance problems. It will make your database much less scalable for reasons that I cannot explain now. Also, if you have some CDC applications that maybe read from your logs, well, they will need basically two things. A timestamp which says when the row was created or last modified, and a primary key which is used to identify the row that has been created or modified. If you don't have that, well, the CDT application will have to do more complicated things, like, for example, using all the columns as a primary key, which is obviously slower. Other bad examples of primary keys are, for example, the email column, because an email can change over time. Maybe you don't consider this when you choose a primary key, but actually it can happen, and it happens. Also, if you do so, the primary key will be a personal information. And there is a problem here because according to the European privacy regulation, the GDPR, and probably several other regulations around the world, in test databases that can be accessed by the developers, you cannot store personal information. So you will have to anonymize personal information by kind of faking it. But you don't want to do this with the primary key because this causes a lot of problems. Other bad examples are, for example, a name, could be a city name, product name, or whatever. Well, basically, in this case, the name will be long, and the primary key will be long. This is especially a problem with MySQL, because in MySQL, every secondary index internally contains the primary key. So if you have a primary key, you will have every index which is bigger than necessary. And of course, less efficient than it could be. Then another example is obviously the timestamp column. Why is it a bad example of a primary key? Well, first of all, it is not necessarily unique, because theoretically two events can happen at exactly the same time. And also it is a quite long column. The length depends if it includes, for example, fractional sequence or not. But anyway, probably you could use a smaller type instead, like a 4-byte integer. Or even if you prefer an 8-byte integer. Usually 4-byte is enough anyway. So another type of key is unique keys. This is also another way that could be used to identify each row, but it's not the preferred way to identify each row. A difference between unique keys and primary keys is that unique keys can be nullable. Okay, they can contain null values. And this is actually very important because you cannot have two unique values in a unique key. So for example, you cannot have two identical emails, but you can have more than one null value. So per unique indexes are columns whose values will always be distinct, no matter if there is a unique index or not. Okay. It is very difficult to make an example here because this is very much dependent on your use case and on your application. But the general rule is if it is impossible that two rows will have a duplicate value for the certain column, well, don't build a unique index on it because this has performance implications. Because every time you change that value or every time you insert a new row, actually the database will have to check if you are going to violate a unique index. This could imply, for example, reading data from the disk and so on. And also, well, okay, let's move on. Otherwise, we will not finish the webinar in 1 hour. So let's talk very briefly about foreign keys. Foreign keys are keys in a table that reference columns into another table. So for example, a user table could have a column called CTID, which has a foreign key, which points to table CT column ID. Okay, it is quite simple. If you think about it, you surely have this pattern in your database, but you don't necessarily have a foreign key. Okay, if you have it, the database will enforce that data in your database will be consistent. So it will disallow, for example, to delete a row from CT if there are users that have a reference to that particular row. Okay. But in practice, you can also enforce these kind of things from your application, and it could be better because performance of foreign keys are typically poor. Why? Well, several reasons, but basically, first of all, the database will have to make every check even when it is absolutely not necessary. Okay. And also, having to make this check will typically read a lot of values that could probably be avoided. It will probably populate your caches more than necessary. And when you run transactions, your transactions acquires some logs, and those logs are possibly propagated over several tables. Also in MySQL, foreign keys have a lot of limitations and they have a lot of bugs. I have written an article about this. Its title is probably MySQL foreign keys bugs. If you are curious, you can look at it. I regularly update it to keep the list of the most relevant bugs up to date. I suggest to take a look if you used foreign keys because some of them are interesting. So talking about regular indexes or secondary indexes, I prefer this term. Okay, there are some bad practices that you don't want to follow. So for example, first of all, don't index all columns of your tables because every index you create has performance implications when you write data. Because when you add, delete, or change existing data, the indexes must be maintained up to date, and the database spends time to do this. Also, You don't want to, okay, you don't want to have multi-column indexes where the columns are in a random order. You need to understand how indexes work, and then you will build proper indexes, because otherwise they will simply not be used in your queries. You don't want to have so-called duplicate indexes, which are indexes that are contained in other indexes. You can see an example. In this example, you will have edx1, which is on email, and edx2, which is on email and last name. Okay, so those indexes start exactly in the same name, but they don't in the same way. They start both with the email column, and edx1 only has that column. So it's duplicated by edx2. In this case, you probably want to drop edx1. The second example is also interesting. It's only about MySQL. It's not about Postgres, for example. If you have an index on email and an ID, well, as I mentioned, in MySQL, every index contains the primary key. It's appended at the end of every index. So if you define an index on email, implicitly it will be an index on email and ID. If you define an index on email and ID, implicitly it will become an index on email and then ID and then ID again, which is useless. And of course, if you have, for example, a unique index on email, you don't have to add another index on email. I mean, the unique index works as a regular index, and there is absolutely no need to duplicate it. Also, you don't want to use non-descriptive index names like, I don't know, ABC, because when I look at the result of an explain command, I should be able to understand which indexes are used, and from an index name, I should be able to understand which columns it contains. It saves a lot of time. Quick indexes. Well, okay, quick hints. Okay, I wrote this article about indexes best practices, but more valuable hint is use this tool from Percona Toolkit, PT Duplicate Key Checker. It basically identifies all the duplicate indexes for you. It tells you what these indexes are, and then most probably you can remove them. Let's move on. Let's talk about data types. So, first family of data types is obviously integers. Some rules. Don't use bigger types than necessary. So you don't want to use, for example, big int, which is 8 bytes, if you just want to store values from 1 to 100. You will use tiny int instead. Okay, but if you are not absolutely sure, don't over optimize. I mean, you will hardly see a performance benefit from using tiny int instead of small int. Okay, it's almost the same thing. Also, MySQL has unsigned integers, which is very good in my opinion, even if it's not standard, because it means that every column can contain the double number of values that could contain otherwise. Okay. So, for example, in many cases, you will be able to use int unsigned instead of using big int. Also, well, I discourage from using exotic MySQL syntax like the medium int type, which is a non-standard thing. It is 3 bytes. but basically 3 bytes variables don't exist in nature, which means that internally in your queries, it will be treated just like a 4 bytes value. It will be probably only 3 bytes on disk, but it's not a big gain, honestly. Also, if you specify int and then parentheses and then length, well, this syntax is deprecated now, and it shouldn't be used because it is not what it seems. If you specify int 10, for example, it doesn't mean 10 bytes. It means 10 digits. And it is not really it is not even a real size because you will be able to exceed this limit when you insert integers. It only has an effect for the MySQL command line client, which will not show more than these digits. It is usually used in combination with zero fill, which basically means add some zeros at the end of the, sorry, not at the end, at the start of the number to make it fit the size that is specified. Honestly, it tastes very old and very strange, and just don't use it. It is confusing. People will not understand what it actually does. So real numbers or fractional numbers. First of all, float and double types are very fast when you need to make calculations on many values. For example, if you have to calculate an average over millions of values, they are faster. But there is a problem. They are subject to approximation. So don't use them with prices or similar data because there is a risk that any calculation will introduce a small error in the decimal part of the number. Instead, you can use the decimal data type, which is precise. It's also slower, which honestly doesn't really matter in my opinion in most cases because I mean it's not a big difference. It's just a bit slower than necessary. The alternative is to use int, which doesn't store the fractional part. So this means you have to multiply the number. For example, you want to store prices. You could have up to two up to two fractional digits. Instead, you multiply this number by 100 and you store it as an int. It works, it's fast, but it could be also a bit confusing. So I don't see it often, and I don't recommend it in most cases. Let's talk about text values. First of all, when you use varchar or char, be sure that the size is adequate to store your data. Okay, so for example, in MySQL, depending on your configuration, if you have a column which is defined as varchar 10 and you insert 11 characters, again, depending on your configuration, it is possible that the value will be truncated. You can also configure MySQL to return an error instead. But in some MySQL versions, this is not the default. In PostgreSQL, there is no difference between varchar and test, except varchar has a specified size, max size. In MySQL, text and blob columns are stored separately, internally, okay? So it is transparent to your queries, but they are written in separate memory pages. So this means that if you run queries that don't read those columns, your query could be a bit faster because it will make less memory accesses. But the opposite happens if you often use, for example, select star, because every time those columns will be read, even if not necessary, and it implies more read operations. The char type is only good for small fixed size data. Honestly, I don't use it because the space saving is tiny, so I don't see any need for it. But if you like it, you can use it. Temporal types, well, they are quite complicated. Okay, so generally, timestamp and datetime are mostly interchangeable. MySQL has a ER type, which is weird because it can be written in two ways, as 4 digits or 2 digits. But if you use the 2-digit syntax, well, its meaning changes over time. Okay, and so honestly, this seems to me weird, and I suggest to just use small int instead. MySQL also has a time type, which is apparently weird and useless, but in practice, it is not really true. It is more useful if you consider it as an interval. So its range is minus 800 hours and plus 800 hours. So basically, you don't consider it as a time of the day, obviously, because days have only 24 hours, but you can consider it as a number of hours needed to do something. But Postgres has a more proper interval type, which is surely more flexible and better. And it's also standard. Also, Postgres allows you to specify a time zone for each value you store. When this happens, for example, when you define a column as a timestamp with time zone. But time zones depend on policy, economy, religions, a lot of things. So they basically change over time. Two persons living more or less in the same place could have a different time zones. The difference between time zones is not always 1 hour. It could be 30 minutes or even 15 minutes. So honestly, time zones are the least rational thing that the humankind ever created after the British Conservative Party. So you don't want to deal with them explicitly. It's a nightmare. Instead, use libraries and store all the values in your database as UTC times, which is standard. Oh, then MySQL has two funny types, which are enum and set. Well, not funny. I mean, I see why some people consider them useful. Basically, they both allow a column to have a list of values that you define. In the case of enum, the column can contain one of those values from the list. In the case of set, every value in the list could be true or false, could be there or could be missing. But honestly, this is a bit weird, not supported by ORMs. There are some very interesting details. So, for example, empty string is always a allowed value. You could specify, for example, 1 as first value, but you can also call it by index. and index will start from 0, just like in an array. So in that case, if you write 0 without quotes, it will mean 1 with quotes, which is really mind-blowing. I don't want to do such a thing, honestly. And also, adding and dropping and changing values requires an alter table, which is typically a dangerous statement because, I mean, it can be slow and it's always possible to make mistakes. Sometimes it is a very cheap operation. Sometimes it can require a whole table lock and a rebuild of the table. It depends on some details, including the version of MySQL you are using. Carl says, I mixed up the definition of enum and set. Yes, actually, yes. I think I did it correctly, but what I wrote is wrong. Very sorry about that. With enum, exactly one value is allowed. With set, any number of values is allowed. So please keep in mind that I switched this in the slide. Thanks a lot, Carl, for pointing out the mistake. So instead of enum, what you can do is obviously to create a separate table with the values that are allowed. We are a bit in late, so I have to go fast here. Another bad practice is to abuse null. Okay, null is also a quite irrational thing. I wrote an article about this, and basically one of the problems is that its semantics is a bit mixed up in the SQL standard. Sometimes it means a missing value, sometimes it means an existing but unknown value, and the result is that sometimes it's very inconsistent. Anyway, what directly affects your queries is what I show here. So as you can see in this example, any operator used with null returns null. Okay, so null equals 1 returns null. Null not equal 1 still returns null. There are exceptions. So is null and is not null are two special operators that are designed to work with null values, but you have to remember to use them. And also, MySQL has a special operator, which is shown in the last line, which basically it is a null safe operator. The problem is no one knows it, ORMs don't support it, and if you use it always, even when not necessary, well, it affects your query's execution, and it could slow queries down. In some cases, it can even prevent the use of an index. So these are examples of problematic queries that are caused by the presence of null values. So all these examples will return null. And it is absolutely not obvious, and it is very easy to make this kind of mistakes and therefore introduce bugs in your applications. So I will not suggest to never use null because there are cases when it is really useful, but there are some very bad reasons to use null, and these reasons are because it's the default. Yeah, it is the default, but it shouldn't. So please always define columns as not null unless you have a reason to. Also, You shouldn't use it to indicate that a value doesn't exist, again, unless there is a more specific reason. Because instead, you can use a special value depending on the data type. So for example, you could use an empty string or -1 or 0 or a special date in the past or whatever. Or another bad reason is to use your tables as spreadsheets. In spreadsheets, you have columns, but you don't have to insert values for each column. But you don't want to do this in a relational database. And probably you are thinking, well, come on, no one does. But it's not really true, and I'm going to show you a couple of examples that are quite common. So an example is, okay, let's say you have a user table with several data in it, and every user have one or more, or maybe 0 or more URLs associated. Okay, so something bad that sometimes people do is to create a series of columns for possible URLs. So for example, here you can have URL 1, URL 2, 3, 4, 5. So if you do this, you will have more columns than necessary, and still, even so, you will introduce a limit that is probably unwanted. So in this case, a user can have up to 5 URLs, not more than that. And it's still a lot, because maybe most users have only one URL, and then 4 columns will be totally unused. So instead, you can have a separate URL column with the URL and with the user ID of the user the URL belongs to. So the other example is you have a user table, and then a user could have a bank account that we know about for some reason, because it makes payments to us or whatever. But maybe sometimes users don't have a bank account that we know, okay? So in this case, a bad anti-pattern is to use some columns that can be nullable, like for example, bank _ bank account number, bank account holder, bank IBAN, and so on. So again, in this case, we will have many columns that could be unused in many cases, which is bad. And also, even in this case, we are still introducing a limit which could be unwanted, because suppose that at some point the product owner comes to you and tells you, okay, we need to allow users to have more than one bank account. What will you do? You will have to move these columns to another table, which implies a lot of changes in your queries, and it's better to do it in the right way from the beginning. So you will have, for example, a bank table which is separate, and it has all the bank data you want to store. And yeah, Dave Stott says, or you can use a JSON document, which is true, but it depends from the use cases, because I guess that Dave's idea is to have a JSON object for each account and have an array of these objects. But this could complicate your queries. You will probably have to index some of those columns. I mean, yeah, depending on your use cases, it could be the good solution, but sometimes not. Then there are hierarchies. Yes, Dave, there are multi-valued indexes. I mentioned them in another webinar. Again, the cleanest and more most relational solution could be use a separate table. There could be reasons to do what Dave is suggesting. So let's switch to another topic, hierarchies. So typical hierarchy is when you have, for example, products which belongs to categories, but you have nested categories. Okay, so the simplest anti-pattern is the first thing you can see here. So you can have a product table with a lot of columns and information, and then you have a category name column, and then you have a subcategory name column. This is the worst pattern, and I hope I don't have to explain why. The following is slightly better. The following is you have a separate category table, and then you have a product table with two columns, which points to the category, which are category ID and subcategory ID. This is slightly better, especially when you have to do things like, renaming a category or other similar operations. But there are possible problems, of course. First of all, to add or delete a level, you need to add or drop a column. A subcategory could be erroneously linked to multiple categories. And actually, if it happens, you are not storing anywhere where what the correct relation between two categories is. Okay, so it could be quite hard to find out which rows are mistaken and which are not. Let's move on. Another better way is you can have a category table, a product table. Again, the product table has a column which points to the category ID, but then in the category table, you can have a parent ID column. So it means that in the category table, you store the categories and the relationships between the categories. Okay. The only obvious problem I can see here is that you could have circular dependencies. It is actually a problem, so you could want to check and avoid circular dependencies on application level. I'm trying to move on. Okay. Another case is slightly more complex when a category could have more parents, more than one parent, okay? Because it is not a tree of categories, but it's probably a network of categories or a graph of categories. So again, this is the anti-pattern. You have category ID and name, and then you have a column with parent ID 1 and another column with parent ID 2. We already talked about similar cases, so you should already know why this is wrong. A better way is to have two separate tables. Category with just the ID and the name, and then category relationship, or whatever name you prefer, which contains a reference to the ID of the parent category, and then a reference to the ID of the child category. And yeah, basically in this way you can store all the parent-child relationships between all the categories. Of course, it is still possible to introduce circular dependencies by mistake, so we'll have to be careful. There is also another anti-pattern. Hopefully it belongs to the past, but you can see it even nowadays. You could have a category table with ID, name, and then parent list, where the list is actually a list of category names or IDs, hopefully IDs. So I hope it is quite obvious why you don't want to have that nowadays. So some things become overcomplicated or hard or impossible. Like, for example, I don't know, finding the direct parent of a certain subcategories and so on. It's You cannot create an index which is good to solve all kind of queries you could have. Of course, you could use a JSON array here in MySQL. You could use an array, not JSON, but just a regular array in Postgres. But in my opinion, it's not a good idea anyway. So let's move on to a very similar topic, which is lists. Actually, we have just talked about a type of list. So you typically deal with lists if you think that they are a simpler way to avoid creating a separate table for something. Typical example is blog posts with tags. Maybe you don't want to create a separate tag table with simply the name of the tag and maybe the ID of the tag. So you just create a post table, and in the post table you create the tag column. So the first query is an example of why you shouldn't. This query, first of all, should look for all the posts that use the sun tag. The problem is if you have a tag which is Sunday, it will be returned by this query. So the second example is slightly better. You basically use a separator, and you add the separator also at the beginning and at the end of the string. But still, it is not good because the select that you need to extract that tag is not optimized. So here you can see an example of how it can be done in a relational way. So you basically add a tag table. In this way, in the future, if it is necessary, you will be able to add more columns to add more information about the tag. Of course, if you think that this will never happen, you could also use the solution suggested previously by Dave, which is using a JSON array in MySQL, or an array, not JSON, just an array in Postgres. You can also index this array, it works, and you can do it, but again, it's less extendable, so it could be better or not, it depends. Just a note, you will have to use the relational solution, this one, in MariaDB, because in MariaDB, yes, you can have a JSON column with arrays, but you cannot build an index on it. Okay, I already explained this. Let's move on. Inheritance and polymorphism. There is really no time to finish this topic, I suspect, but let's start anyway. First of all, a problem that occurs sometimes with relational databases is when you have different entities which are not so different. So for example, your database may have users and landlords and tenants, And they are separate entities with different information, but sometimes you also want to treat them as a single entity. So what to do in this case? Well, you can use inheritance. So in the simplest case, all these types are just subclasses of the same thing. For example, landlords and tenants could be types of users. So you can define a parent class, in this case user, you build a table for user, and this table has all the common columns that are meaningful for all types of users, including landlords and tenants. And then you build separate tables for the subclasses. So you build a table landlords with the columns that only make sense for landlords, and you create a table tenant with the columns that only make sense for tenants. Postgres allows to do this in a much better way, which is called table inheritance. You may want to take a look at it in the Postgres documentation. I will not explain this in this webinar because it's a bit out of the scope. So anyway, a problem with this pattern is that, again, sometimes you want to consider these entities as a single thing. So a typical anti-pattern is to build a union view, which basically is a query which returns everything from the landlord table and everything from the tenant table. You can see the syntax here. But it's potentially very slow because probably the database will have to run this query completely, materialize the results, so materialize all the content of the two tables, and then run the rest of your query on the materialized information, which is not good. So let's say that a reason why you may want to treat sometimes landlords and tenants as a single entity is that maybe you want to guarantee unicity over a certain column. Okay. So before talking about this, ask yourself, is there a practical reason for that? I mean, is it really possible that someone tries to register as a tenant and then as a landlord, and this is an actual problem for you? If not, don't deal with this theoretical problem. But let's talk about the case where you actually need to deal with it. So in this case, you're probably thinking about the problem in a wrong way. So if emails need to be unique, then they are actually a separated entity, a unique separate entity. So you will need to create an email table with the email and an ID, and then both landlord and both tenant will include, the other way around. The email table will include a landlord ID and a tenant ID. But this solution initially looks good, but linking emails to landlords or tenants in this way is quite horrific. So what can you do? Well, first of all, why? Well, because you cannot build, for example, foreign keys. Again, I don't recommend to do it, but maybe you want to do it. You should theoretically be able to do it. And also, in the future, you may want to link emails to suppliers, employees, whatever. So in this case, you will need to add more columns to the table, and this is not good. So what you can do instead is basically almost what you did, what we did before. We create another table, which is not a superclass in this case, but a superset. We have a person table with the IDs of all the landlords and the tenants. Well, I simplified a bit. Maybe we will have to add another column to specify if this is a landlord or tenant, but I didn't want to dig too much into things. So in this case, anyway, I hope you see that we can solve the problem we mentioned, because we create this separate email table, and this email table has a person ID, which links to person, and then you will be perfectly able to create a foreign key if necessary. Okay. So we already exceeded 1 hour, which is a pity, because I cannot mention another very interesting topic, which is building a catalog of different products with potentially different columns. But fortunately, this is something I covered in a previous webinar, which is called, I believe, MySQL. No, sorry, it is called JSON in MySQL and MariaDB. If you look at it, you will see solutions for this kind of problems. So I don't want to skip directly to the end, so I will briefly show the last slides, which are about miscellaneous anti-pattern, mostly about naming things. First of all, this is actually from the real world. In a company where I worked, I saw production tables with these names. It was very interesting because Marco and then an year was actually the name of the person who created the table, and then the year when the table was created. And then there was also Jan and then year. And then you may think it was created by someone called Jan, but no, actually in this case, Jan was January. And then there were also these very interesting names, temp, fix, and then also temp, fix, which is kind of symmetric. There were probably more examples I saw even in other companies, but I forgot them because as Lovecraft wrote, ultimate horror often paralyzes memory in a merciful way. So you want to avoid this. You want your tables to actually describe the content of the contents they're storing. Okay. Why? Because your people will join the company and they don't know your database. They need to look at a table, and if what the application do is clear in their mind from the table name, it will be more or less clear what the table contains. Okay. Another anti-pattern is to include data in table names, or if you prefer, include data in metadata. So, for example, invoice 2020, invoice 2019. In this case, the year of the invoice is contained in the name. This is very, very bad. You don't want to do it. Instead, if you have a single invoice table whose size is growing too much, well, you may look at other options, which basically depend on the database you're using, but the idea is always the same. You want to partition the table, but you do it in a way that is transparent for application. If you are looking at this webinar, you probably are not a DBA, you are a developer, so talk to your DBA, they will hopefully know what to do. But names in general are bad, of course. Again, because a table name should describe what the table is, New hires should be able to understand what a table is from its name. You also should be able to understand this in 5 years from now.